Same. I hope this lesson is done. This is learning that they get to learn. Because some of you, I think, it is completed. Yeah. So, please do that TA part tomorrow. You can do your 5 days, right? You can do all the day by afternoon. You know, open that result section. Yeah, now it is green. It will disappear automatically. So let's continue. Go to that whatever you input you have provided, and the result section. In result section, you first check the SCF energy. So it is 7 iteration was done for that SCF calculator. And for the optimization, it is taking 5 iterations to complete the superset. So though your calculation is still running, let it be, but you please open that Excel sheet. You can use that energy. Open Excel sheet. We are going to calculate the cohesive energy. Anyone? What is cohesive energy? Anyone? Actually, it is the extra force that is able to bind the copper or whatever the element is there in a specific lattice format. Like for the copper, it is binded in the FCC lattice format. So what are the extra forces required to bind these individual atoms? That energy is called the cohesive energy. It is due to the cohesive energy, it is intact as a solid surface or solid lattice. So that energy we are going to calculate. So before this, open that copper for optimized sector. Open the copper for optimized. Go to the recently used tab, and whatever the copper for optimize is there, you just double click. Okay. Go to the optimized copper lattice, but copper core lattice, not the 32. Copper core lattice, and set its cell length is 10 angstrom. Actually, we are calculating the energy of single copper atom in vacuum. First, we are calculating the single energy of single copper atom in a large cubic cell of 10 angstrom. So set is as a 10 angstrom. Since we required only one copper atom, so delete 3 copper atom. Right click and delete. Right click and delete that atom. 3 atom, only one atom should be there, and you can set your box in between your gray tab, and you can see that the unit, the XYZ coordinate for it is in the angstrom, or it is in the Cartesian coordinate. So you just, for the convenience, we set it to the crystal type so that you can use the fractional coordinate, right? Yes. And in the that part, we intentionally keep it as in the center of that box. We are calculating the single atom energy, and we are putting that single atom in the center of the box.
So I have taken the corner one.
No,
So
whatever you just delete this 3 copper atom, we will set the coordinates for this atom. It is due to the periodic, it is saying 2 atom, but it is 1 atom. And change that uh, crystal part, not the angstrom, right? And write all coordinates 0.5. 0.5. So it will be coming in the center of the red box. Change the atomic type of that coordinates to the crystal, and set all coordinates. Just double click that part, coordinate part x, y, and z, and write 0.5 each x, y, and z direction. Put 0.5 and press enter. If you are not putting enter, then it will again come into the same. Double click that box. Double click. It's all 0.5. So what we are doing? First, we are changing the lattice constant whatever it will be, and change it to the 10 angstrom. Elemental part same because the same copper atom we are using, and in atomic part we change to the geometry part into the crystal type, not the angstrom unit, and set that 0.5, 0.5, 0.5, right? So it will be show a one copper atom centered in a box of size 10 angstrom, right? Everyone is following this? In the coordinate of then you could mix it. First time. Yeah. So after this, you go to the SCF tab and set K point as 111 because we are for single atom you don't require that too much K points in the brilliant zone. So 111 is enough for single atom. And for optimized part, I think you have variable cell. Yes, just do it as a no. We are not optimizing the cell. We are only calculating the SCF energy of the single copper atom placed inside a box of 10 angstrom. SCF. So I think you change that K points to 111. Now check the input file. It is showing SCF with A as a 10 angstrom. You can see that. Here you can see K point is written as gamma because we use that 111. So by default it is a gamma. Now go to the run this job as a SCF. Job type should be SCF. But before this, please save this as a different file name. Otherwise, it will overwrite. Save as single copper 10 angstrom. Before this, save as different file name. Otherwise, it will overwrite your copper 4 calculation, right? After saving, you just give its run as SCF, and so it will not take much time. If it is showing red color, it is calculating. After calculation, it will show the green color and disappear from this tab. Yeah, it is done. Okay, so in the everyone's optimized, right? We are only interested in the SCF energy, right? Now open the Excel sheet. So it is the energy of single copper atom. You can see that it is a minus 1.22.387. This is your energy in your case. Similar.
That's 122.878.
Yeah, since potential is same, it should be same. But if slight variation is there, then it can be neglected, right? So you just copy this part. I think better write 1 minus 1.122.387 for the single copper. Yeah. And we are calculating the cohesive energy first for we are calculating the energy for the copper core system, right? If your file is missing, then you can use that energy what we are using here. So go to that again copper core optimized system, and again the result tab and SCF tab, and this energy, whatever energy is there. Everyone is following? Now copper core. Yeah.
You'll see the minus
Okay.
one.
So here the energy of copper core system is 490.34387. So since it is a single copper energy has this one, we have number of copper core, so we multiply the collective amount energy. So it will be 4 into. Just multiply the 4 and this number single copper's energy, because we are calculating the cohesive energy for copper core system. So copper core system has 490.344 energy, and since it is made for the 4 copper atom, and we already calculated the single copper energy, and number of copper is 4, so we multiply that 4 into the single energy, and take after multiplication we will take the difference between copper system and its individual atoms for contribution system. Okay. Since this energy is in that Rydberg, and we have 31 Rydberg equal to 13.6 electron volt, right? But note that in for defining cohesive energy, it is the energy per unit atom. So we should divide this energy by 4 as well, because we are getting energy. We are targeting to find this energy in terms of energy per unit atom. So it has 4 atoms. So not that difference part, not the earlier part. So we are dividing this by 4 with 4, right? So this is the cohesive energy in Rydberg unit. But for electron volt, we need to multiply this into 13.6. Everyone is getting that cohesive energy for copper core system.
Difference, sir.
How much?
Mine is some minus 2.55.
Can be possible because pseudo potential is not good here.
Oh.
Even it is this minus 2.7 is too much deviated from that experimental value. Anyone knows the experimental value of cohesive energy for copper? Anyone? Earlier I saw the slide that I mentioned. Minus 3.48 or 49. So this way you can find that how to calculate the cohesive energy for uh, whatever your system is, either aluminum or copper, iron, whatever the various latest is there. You can calculate the cohesive energy. So this is the basic governing equation that lattice bulk energy, either you are using for copper core, or you can use the same equation for the copper 32. Here the energy of copper 32 will be there, N will be the 32, and single atom will be the same, and you will take the difference. And
Then you will get the cohesive energy for 32.
yeah, so for the ideal case, it should be matching. I'm showing one of the results. So definitely it is the result of WASP system. These all are calculated in the WASP. That is why its energy is matching too much to the experimental values. Here we are using the pseudo potential value and in Burai, that quantum espresso. But in the WASP, we have the power potential. You can see that power potential is used. That is why for the 2 cross 2 system, it is a 32 atom. Single copper energy in electron volt is this one, and lattice bulk energy for different system is will be the different, and cohesive energy for overall. But generally, it is reported in terms of energy per atom. So it will be consistent. Either it will be the 2 plus 2 system or 4 plus 4 or 3 plus 3. So it should be consistent with the values. So in the from the experimental value it is 3.49 and the calculated value from the work is 3.48. So you can see that how the pseudo potential is affecting our result, right? So now I'm moving to the other part. Just open the again the optimized structure of copper 32. So earlier equation was calculation was for that super cell. You have unit cell copper core. You had make the super cell. You can make larger super cell like 4 plus 4, and sometimes if you required bigger, but depending upon your system, you have to choose what super cell you require. Now we are going to construct the surface from this super cell. So again, go to the modeler. This time, instead of supercell, go to the slab model and choose the Miller index. So here, first use that 100. Anyone have idea what is Miller index? Yeah.
But if I want to take it in terms of plane along which other axis?
Yeah. So it is a plane actually. So 100 means it is along x direction 1 unit and y and z direction is not. So it is plane 100 and build this plane. For that part, I am also showing what is exactly. This is the Miller index for this cube. You have 100 plane for in FCC like that yellow shaded part, and 110 plane in it is diagonal to that part, and 11 plane is the triangular connecting the all diagonal of the faces, right? And in the worst, you can see that the brown one is the lower surface and upper part is yellow one. It is highlighted. That is why it is showing the arrangements of atom in this. So we have chosen this time 100. It is looking like this square shaped all atoms. So here whatever you have made, you can see from the top. For the simplicity, here you can adjust the number of layer and set it to the only one layer. Right? Here you select this cursor and slide to the lower value. So it will change the number of layer. So this way you can see that it is a one layer. From the top view, you can see how atoms are aligned. Right? Are you able to find this? Any question? Okay. So first we will do the second two layers system, right? Two layer system. And before this, you better save as again as a copper two layer, right? So make always make sure that we are creating surface from the bulk system, right? We have taken that copper 32 and it is elongated along each direction two times. Earlier we have found. That is why you can see that its lattice is two times of the whatever the its original lattice 3.8 is double. So this time we should not alter this value, whatever it is. You can see total 16 atom is there. Yeah, this time we can say
Reset here, what? For the reset here.
Please say it as
Z go to the
yes. First save it as different copper to layer, otherwise it override the copper 32 calculation. Go back to the slab part. This one. Go back to the slab part. Click on the next arrow. Yes. Yes. Reduce that to the two layers. And open this atom part, you will see that some part is blue colored and some is in black color. So blue number it is also mentioned that these coordinates are fixed. So generally for surface calculation, we generally used to fix that lower surface to save the computational time, right? If you have more layer, then suppose you have 5 or 6 layer, you can freeze that 3 to 2 layer, and upper layer you can keep it as relaxed. Blue part is fixed, and total 16 atom is there. So you can quantify that in one layer, total 8 atom is there, right? You just save this part. Again, we are going to construct another plane, right? Save and close this part. Again, open copper 32. Go to the modeler, slab model. This time you should put 111 and build that model. Right? This time you put a 111. So you will, if you select to one layer, so you will see like that. This way you can see that it is a one layer. From top view, you will have a diagonal shape structure. Everyone is able to find this slab 111. In the slab part, you write the Miller indices 111. You can see it is like diagonal shape part, like you are seeing. For the 1008 is a square type structure. Actually, you can see that it is a, if you increase its if you increase its layer, you can see ABC pattern. You can see that after 3 layer, same layer is repeating, right? So this time it is vacating from this side. If you select this one, so it will going just opposite direction. It is the same. No, it is same. Like here in the top layer, you can see it is this way. Then it is showing this direction way, and it is switching just opposite direction. It is only the direction, because you see the top layer in the same case, it is showing 4 atom system. Here it is showing 5 atom system. So it is just the periodic system. So it is not a different system, but direction of view is different, because you can cut either from this part or from this part, right? So this is cut from that 5 layer part, which 5 atom part, and this one is cut from the 4 atom part. So it is same, that is same number of atom will be there in that if you calculate the in each layer. So it is the only visualization. Suppose if you want to place a molecule which require large surface area, so that time you require this part, large surface. You can extend the surface also, but it will extend the number of atoms, right? Okay. So switch to is this time we will do it for the 3 layer, right? Make it a 3 layer system. And also, since it is a periodic system, so whatever box size you are see, you can assume a similar box nearby this, similar box up and above in all directions. That is why if you are doing the surface reaction over that top surface, so if you are reducing this box size, suppose this one, that means if you are placing a molecule here, so suppose this direction is 0.5 angstrom, here also 0.5 angstrom. So between same molecule, you will find a 1 angstrom's distance. So it will create a interaction between the same image. Because the periodic system. If you are placing a molecule here and distance between surface and molecule is 0.5 angstrom. And same is here because it all are structure is repeating. One more structure is above in this side and this side in all directions. So you are basically doing the it will create a additional interaction between the same molecule and also with the same surface. In other words, you can see that this layer and this layer you can it is not taking this distance for the interaction, but from this direction. Suppose this distance is 3 angstrom and this is 0.5 and this is 0.5. So distance between this and this will be considered as the 1 angstrom due to the periodicity. That is why we are keeping that vacuum space so that we have enough space and we are not having the interaction among the molecule, but the between the surface and molecule, right? So in this case, if you are putting a molecule here, then this additional distance, then if this distance totally will be the distance between the two similar molecules. So it will not give the additional interaction between the molecules. It should be more than 10 angstrom better for that repetition of repeat interaction. So this time we will choose that 3 surface for this slab model and save it as like previous. Again, save this as with different name. Okay. This time you can see that how many it is. Yeah. So in that 1x1 plane, number of copper in 100 plane is 8, 110 is also 8, but this is a dense plane. You can see that how the atoms are closely packed, and it is forming a triangular shaped structure between the atoms. That is why it is the number of copper is here in this case 16, not the 8. So for 3 layer, total number of atoms is 48, right? For the specific atom, if you want to, like earlier I mentioned that it is blue color showing that it's this atom is freeze. But for the specific atom and the specific direction, if you want to control the movement, you can right click this one and X mobile means in X direction it is relaxing, right? But in the specific case, it is along Y and Z direction. It is itself it is freeze, right? So you can freeze this part also, Y mobile and Z. But you cannot do like this for the every atom, right? So you check its input file here. So everything is fine, but once you scroll down, those atom who is freezed, you can see that a 0 0 value is there. Default value is 1 1, but if it is not written, it is considered a 1. 1 for that it is relaxed in all direction means direction. It is 0 in 3 directions. That is why it is split in all 3 directions, right? So you can either here you can remove these coordinates, and either you can take all these coordinates in the Excel sheet and remove this 0 part and again paste the only coordinate part. You're able to do. Just Control X these coordinates. Open new sheet and change its separate its with the space values. I think you know this part. So it will have all this separated column. Copper is there and XYZ coordinate is there, right? And bottom you will see that this part. That is the reason it is showing that it is a freeze coordinate, right? You just delete this. And again, you copy this all. And paste here. It will showing some rearrangement of that. That not an issue. And whatever you have changed in the input file, you just redirect the change by clicking this arrow and see the color for that. You can see that all blue color is disappeared from here, right? That means all structure are now able to relax. No atom is freeze. Copy all coordinates in the Excel sheet. Extract means separate this column and remove that 0 0 part, and again copy this part and paste it here and press this icon bar. So whatever input you change here, it will change in that also.
Control, control, electron, next, वो system control दबा के पूरा स्टोर करना और मोबाइल करने के बाद
Okay.
control दबा के
One more thing, I have to check first. Yeah. Now, those who already done that Excel sheet is fine, but you can do in a shortcut way. Type here. I have done all atom as a fridge, like you are seeing in all atom in the blue. So all atom are fridge. Now you can press the control from the keyboard and select all atom here. Right? Select all atom and right click and let's select all atom as mobile. Since you are already mobile, so you can select as a fixed. You can switch either mobile or fixed. So here it is all are fixed. You can see that in blue color. So after this, you will see still 200 is there, but you have to refresh this tab. So you will see that a 00 is disappear and also it is all are related.
How to select it?
Control and mouse. Use your control button and mouse using the mouse drag. You can select all atom. And after right click, you set as other. I'm doing again, right? Control like this. Right click, let selected atom to be fixed. All are blue color, but here in the to see the change in the input file, you have to refresh this tab. So it has two things. Like if you are changing anything either here or here, so you have to refresh using this button. It will appear here. And if you are changing here something, you have to redirect from this button, so it will change this system. So both way you can change. So this time again I'm setting all mobile. Okay. Actually, I'm not doing the calculation. You can, after making surface, you can do this calculation because it will take too much time. And during calculation, you are not able to make the new file. That is why I'm not giving the calculation, but I'm showing what are the different calculation you can do. Like how to make the surface. Already we calculate that how to make the supercell and then find its cohesive energy. This time from the surface you can make calculate the surface energy. It is already done. So this way I am showing you the other result because calculation you already see that how optimize only copper 32 atom is taking too much time, right? So whatever layer you have choose, so either 4 layer, 5 layer, 6 layer, 7 layer, you better to avoid the means save the calculation types. You pick the bottom layer because you are interested in finding the catalytic activity on the surface. So if you go down to the surface activity will be reduced and bulk property will be there. If you are interested in surface activity, then why you are going to calculate the all atoms energy? That is why we are fixing that 2 layers, sometimes 3 layers, depending upon the layers. So in my case here, I have taken 4 layers, which is having the number of atom here. You can see 32, 40, 48, 56, and after optimizing, you will get the energy. This one, and this energy, cohesive energy, bulk cohesive energy, you are taking from that previous calculation. So after this, in this case, you can see that surface energy can be calculated using this expression, that energy of system that you are calculating for each slab or layer, and single copper energy you already calculated. Number of atom you already mentioned depending on the layer and depending on the which surface you are cutting. 100 have in one layer 8 atom. 110 it also have the 8 atom, but for the 111 it have in layer 1 it has 16 atom. That is why for 4 atom 8 into 4 32. Similarly, following the same trend. If you take the other surface like copper 111, it will be the multiple of the 16. So we will take the difference of this part and divide the energy with the area of the surface, because in each case area will be different, like you can see. For the it is for the copper 3.63 cases, like after doubling it becomes 7.286. So you can calculate the area by taking the square of this. Same for that 110, but this time the area will be this yellow plane, not this one. So it has different area. And for that 111 plane, you have to calculate the area for this. And apart from this, you can calculate area also from that. During calculation in the log file, you will find a volume of this lattice, right? During calculation, you will find the volume of lattice, and you just divide the length along that direction. So volume by length is giving you the area, right? So in two way you can calculate the area. Either taking the area of calculating this, because this is not a simple here, it is a triangular part. You have to calculate using that triangular area part, because it is along y direction. You are seeing that it is not aligned to the this axis direction. Y direction is not aligned with the lattice direction in this case. So anyway, after calculating area, you will able to find that surface energy unit is electron volt per angstrom square. So it is for the one system and with different layers. You can do it for the another surface with different layer. Here you can see that similar to that that cutoff calculation, you find that the difference between the 5-layer energy or 4-layer energy, and between the 6-layer and 5-layer and 7-layer and 6-layer, you will find that it is in the milli electron volt. So here in this case 0.1 milli electron volt is there, so that is enough for that because this is too low value, it is milli electron volt. If you take more layers, again your calculation time will be more. So better to take the, if it is coming too much less value between the energy value between the two layers. So this time, since you can see that between 5 and 6 layer, you are having only energy difference of 0.1 milli electron volt. So what should be the layer? We should choose 5 or 6. Definitely 5. Because in 5 you have 40 atoms, in 6 you have 48 atoms. So it will save your time, right? Since we are not having too much time, that is why we are not calculating this one. But we are giving the idea what you can do, what type of calculation, how to make the files, how to make the surface, how to put that. Now we are interested in suppose you want to put a molecule over there, this surface, right? But this time, since it is the limitation of this software, in other software you can import the XYZ file of whatever the molecule is there, and you can move or rotate or place in your choice. But this case will anyway we will do that. Just stay this way, and suppose we are interested to finding this at this point, at which height you just right click mouse and add put an atom. So for monoatomic atom or the diatomic system, we can do, but for the large like benzene, in this software you cannot do. Other tools or other software is there. You can import the XYZ file or download the CIF file. But here we will use that H2 over this surface, hydrogen molecule over this surface. So select the hydrogen. So you can see one hydrogen atom is there, right? Just right click on the top and put. Before this, I want to highlight some. Just have a look on the nature of surface. Like for the 100, you have this plane already solved. So it has, you can see the top layer. It is having copper, and here also one copper is there. But above this, just I have put at one oxygen atom, right? So this. Yeah. So I am putting oxygen over a just above the copper atom. Below this one copper atom is there, and this position is called the top position, right? Top position with respect to the copper atom, because we are putting oxygen over the copper. And when you are putting in between two copper atom, it is a between two atoms, and it is called a bridge position. So it is a different means a position in which you can study the absorption of this oxygen or whatever the molecule is there or atom is there. So it is the bridge position, and when it is in the four centered hollow part, it is called the hollow of this part, right? So depending upon that position, you can find that which among these which one is the stable position, either top position, bridge position, or the hollow position. So the thing is, just put your atom at the specific position and optimize the structure. After optimization, you check the energy, whatever energy is there, and if you have more negative energy, that means it is a more stable position. So definitely, here in case of hollow, you have more interaction of oxygen with the four different copper. So that is why it will show a stable position in general, right? So it is a different position I am showing you. Same for that 110. Top one is this one, bridge is this one, hollow is this one, uh, and for that interesting is that this 111 surface, because it has the triangular shape geometry, and you can see top one is this one, and in bridge it should be this one. It is actually optimized geometry, that is why some distortion is there, and it is the hollow position between three copper atom. So up to this, any confusion is there? What is why we are talking about absorption? In the earlier session, Musarraf sir said that absorption studies can be used for the storage, either hydrogen storage or surface storage. So that time you have to choose that which place we have to put. If you are putting on the top position, then it will not hold for a long time, right? But for the hollow position, it will hold for a long time. That means for that storage application, this part will be the better position. And this you can quantify using the absorption energy. Definitely, absorption energy in the hollow position will be more compared to the top and bridge position, because the interaction of the atom is more there, right? So I'm just giving one idea that how binding energy is calculated. For that, it is the position of uh, oxygen atom with respect to copper. It is top, bridge, or hollow. We already discussed what is this position, and calculate the combined lattice energy, right? And since you are working with O2 either with H2, you just calculate the O2 energy in a vacuum large box, like we calculate for the copper, right? Earlier we have calculated the energy of single copper atom. So this way you can calculate the energy of single O2 molecules. And if you divide, uh, since we are absorbing only one O, so you can take the half of energy this one. The bulk energy of O atom is this one. either H atom, it will be different, but energy you can calculate by the same procedure. And it is the energy of combined system when oxygen is absorbed in the box position or the hollow position. It is a combined energy, and it is the lattice energy of pure surface, right, without oxygen, and it is the combined system with oxygen. Either way, it will be top or bridge or hollow, and we'll take the difference between the final and minus initial. So it will give the binding energy. This, right? So depending on the magnitude of binding energy, you can see hollow has more negative values. However, there is a calculation mistake. That is why we put the star in this case. It should be generally hollow has the more negative energy than the bridge and top. So we can say that the hollow one is the more stable and more applicable for the any application, either in the absorption, for the sensing purpose, or for the storage purpose, right? Yeah, same I have done for the other surfaces. You can see that this is the energy variation. In this case, it is coming good. That for top it is -20 electron volt, for bridge it is -21.2, and for hollow it is -21.9. So this way you can find the binding energy. Either it will be your gaseous molecule or some means a big molecule, either a benzene type molecule. But in this case, we cannot add that means molecule. We cannot add in the this tool. Burai, in this tool we cannot add directly, but we have to tune this. So anyone know how to add the H2 molecule there? It is the single atom you have added, right? How we should add the H2 molecule? Anyone, what is the bond length of H2? Bond length for H2 hydrogens. Take the literature. So I will add another hydrogen just nearby H2. So it is not a means I have added, it is forming by bond by own. So make sure go to that tab, atom tab. You have atom, two hydrogen is added, right? Two hydrogen is added. So definitely, if you are your molecule is coming from the above surface, so हम लोग we cannot decrease that means we cannot have the difference in the Z level. So we can use the same Z level. Either it is 16.7, so we can put it at 17 and 17, right? 17 and 17, you can do that. But here interesting thing is that you can see that the lattice plane direction is not in the same direction as x and y. You see this. This direction is not aligned with the x and y direction. So in this case, some mathematics will be involved, but I am not going to discuss with. I will take the other simpler system so that you will not get confused. How to add the whatever you have done, just save this again. Save this. Yeah. Now open that copper two layer system. Okay. Open again the copper two layer system. And again add two hydrogen nearby. This time, generally for the physio's option, we generally take the distance 3 to 4 angstrom between the surface, top surface, and the molecule, target molecule. So you can see that its value is top layer is 12 point something. So you better to choose it is as a 15. Put the z coordinate to 15, and this it is a plane of 100. That is why its axis is all axis is inclined with the real axis. That is why we can change the coordinate freely. So you can again keep the y direction same. Hopefully it is same. In my case, it is also same. So if it is same, then not required to change. If in your case y coordinate is same, not same, you better to write this one 3.61. And for simplicity, we are changing one of the coordinates to 3 angstrom. And from literature, we know that the bond length of H2 is 0.75 angstrom, right? From the literature, you know that the bond length of H2 is, that means in H2, the distance between the HH is 0.75 angstrom. So you can tune here, one, all two coordinates are fixed, and the inclined axis is uh, similar to that lattice axis. So you only change this one. So it is 3.75. Are you getting it? The distance between the hydrogen is 3.75, and you can see that x, y, y, z is same. Z we have to keep fixed because we are coming from the top, and x, y is also I have fixed because I have to change only one direction. If you change both coordinates, otherwise you have to do that under root x1 square y1 square to be the 0.75. For the simplicity, we kept two coordinates as the same, and only one coordinates are varied, which is the difference of 0.75. Any confusion up to this?
But now the bond, hydrogen, the bond.
That is the visualization issue. After optimization, they will come. Even if it is not showing, but it will be remain intact. Whatever the interaction between hydrogen and hydrogen is there, it will be available. So it is the means the designing of this specific software. In some software, you will see some bonds, some software it is missing. So it is not that, because in periodic or this type of calculation, they are not recognizing any bond. They are only considering the electron cloud and the interaction between the atoms, right? So this way you can put the simpler molecule over this. But in other software, which other some paid software is there, like Quantum ATK. Anyone has used Quantum ATK or Mediavas like this? So in that type of software, you can make a separate XYZ file for that part, and you can import in the box and rotate and incline and molecule and put in that. So in this case, we will for the simpler molecule we can do like that. And I already earlier mentioned that for the large system, large layer, you have to fix the bottom layers so that it will reduce your computational cost, but it will give the whatever the top surface and second top surface is, the catalytic activity or the interaction energy will be given by the surface. Okay, so this way you can calculate the interaction energy between the molecule and the surface, or the with in presence of surface, you can calculate the binding energy with the distance. If it is on the too far away, like in the physios of surgeon, you will get another interaction. If you are putting the molecule closer to the surface, it will show another interaction. Maybe sometimes it will get dissociated, right? So from this way, you can also study the dissociation of the molecule over the surface. So it is but it is a step by calculation. For example, initially you have hydrogen molecule at the 4 angstrom level. You have to calculate the energy, and again you have to reduce like 3.5, 3, and this time if you see that with the catalytic effect with the surface interaction, it is getting dissociated. Initially, it is bond is elongated, and when it is too much close to the surface, it is getting dissociated. So I am showing only you the pictorial view for that, because without calculation we cannot conclude that part. So here it, like initially it is for the copper and oxygen system, you can do for the hydrogen as well. So it is the initially oxygen is there when it is coming placing above the 4 angstrom. Here the bond length of oxygen is there, optimized system. It is the side view and it is the top view. You can see that. And our target is after reaching to the surface, these two hydrogens should sit on the these two stable hollow position. Are you getting it? After reaching to the surface, it should sit on that stable, because we already discussed that top and bridge and hollow position is there. So definitely whatever the most stable site will be there, it will sit on that place, not on the top place, but in generally in the uh, that hollow position. So it is a one animation that how it is getting dissociate. So it is the initial position where that oxygen molecule is here, and it is the final position after the dissociation. So I am repeating this part. Yeah. So it is coming, and after elongation at a certain level, it is getting dissociated and sitting on the surface. It cannot by one going inside the surface, right? Because if it is going inside, it has more interaction, more positive interaction with the molecules. So it has some repulsion. So based upon the stable inside, it is sitting on that. You can see that the final position, top and the side view after the dissociation, and you will get a similar curve. Like here I am mentioning that for the 110 surface, with the distance, it is bond length between the oxygen is initially 1.21 or 1.25, but when it is reaching close to the surface from 4 to 1.5, it is suddenly start breaking and becoming stable to this position. Are you getting this part? Actually, it is a more lecture part compared to the hands-on session, because you observe that how too much time is taking in that calculation. So if time permit later, we can do more problem. But I'm giving you just basic idea when you are working either in your place, that what type of calculation, how to make the system, and what type of calculation, what type of analysis you can do, right? So similarly for the different surfaces, it is showing that in these surfaces it is breaking at 1.5 angstrom. At these surfaces it is breaking around 1.75 angstrom, and this surfaces around 2. So depending upon the activities, because here the planar density is very high, that is why it is breaking just above the surfaces. But here planar density is low, that is why it is taking much closer, I mean so much time closer to the surface, and then it start breaking. So this will the analysis. So I am just explaining that it is apart from this dissociation, you can also study the diffusion part, right? Like it is a non-interacting zone initially, and after this, at some level, it is a molecular absorption level. and when you keep moving that molecule toward the surface, it is starting dissociate. And after dissociation, if you have the large concentration of oxygen or hydrogen over the surface, due to the concentration difference, it can now, due to that concentration pressure, or you can say the potential, it can get it inside the system and diffuse through the system. So that I already mentioned that why we are freezing that part, because here the surface phenomena is very less, but the bulk phenomena is there. That is why it is called as the bulk diffusion in this region, and closer to the surface, it is the surface diffusion. And after coming from out from the surface, it again associate and and make the bond again after the diffusion. So this way you can do the catalytic activity. Generally, the formation of the radicals, when you are putting the molecule over the surface, it form a radical, and you can do the surface reaction here. If the concentration of oxygen is not much, you can do the catalytic activity in the surface. I am showing you just last animation. I think it is for that hydrogen permeation inside that iron surfaces, how it is going, and in which way it is following the zigzag path, because it has to follow the uh, stable pathways. And after the dissociation, means sorry, surface diffusion, and it is coming out to like this. So this is the last one, means it is showing that level, that which one is the molecular dissociation adsorption level, when it adsorb, how it is getting dissolved, all these things. So it, and these all are totally related to the surface phenomena. And if you are showing that diffusion, it is a bulk phenomena. So this type of analysis you can done later. So I think that is enough for today. I don't know how much you have. Yeah. Yeah.
Why the molecule?
Yeah, exactly. Because it is the non-impacting loop. When it is coming to the air surface, then we can have power reflection and in more level compared to the accelerator. That is why it is like getting speed.
Is there any small parameter?
Yeah. You can say you see only atom which is the optimized atom. It is taking too much time, and you already modified and cutting the surfaces and optimized. It will take more time. So we generally calculation we are based on the supercomputer, not in the even the workstation and the require supercomputer. So that Gaussian part, which is the gas state calculation, that you can go in the for the smaller machine, but for that periodic system is very difficult. Sometimes those who don't have any this facility, they are running for week. For 1 week, they are getting one result. So think about how they will dissociate on the surface, because it will take too many steps to dissociate. Any question? ठीक है सर इनका Yeah, we are making yeah, for those they can So, this is what we discussed in the I hope this was a good session on this pyramid DSP. So, I once again thank you for saying, and also Iman for conducting this hands-on session. Thank you.